You were taught that a computer does only one thing. It processes information step by step, bit by bit, according to a clear logical sequence, an idea that has existed since the 1940s with machines like the ENIAC. It sounds reasonable. And for most of the history of technology, that was true. But then, when Google announced that they had achieved quantum supremacy with their Sycamore chip, everything started to become very strange. A specific problem was solved in about 200 seconds, while the most powerful classical supercomputer would have taken up to 10,000 years. This is not just faster. It is not that simple. Because if a calculation exceeds all familiar computational limits, then the real question is no longer how powerful is the computer, but rather how is it doing that? And more importantly, where is it doing that? And when you follow that question far enough, you begin to realize that the problem is not in the technology, but in our very understanding of reality itself. What makes this story serious is not a technological record, but what that record implies. The results from Google's experiment are not just a technical advance, but a direct challenge to the way classical physics describes the world. The problem they used, called random circuit sampling, has almost no immediate practical applications, but it is extremely important theoretically because it exposes the limits of every familiar computational model. A system with 53 qubits can represent up to 253 states at the same time, a number so enormous that it far exceeds the storage and processing capacity of any classical computer. Now pause for a moment and think. If you need to consider a state space that large, one that even exceeds what can be directly mapped onto matter in the observable universe, then where is that calculation actually taking place? A classical computer would have to check each possibility one by one, sequentially, consuming resources exponentially. But a quantum computer seems to process that entire state space in a single evolution of the system. This is not just a difference in performance, but a direct violation of our intuition about how physical resources are used, about how space holds information, and about how a process can exist in the physical world. IBM later offered counterarguments, claiming that classical supercomputers could simulate the results faster than the initial estimates. But even those counterarguments do not deny the core nature of the phenomenon. The quantum system is accessing a state space that we cannot represent efficiently with any classical model. And that is the point where everything starts to become uncomfortable. Because if you follow this logic to its end, you are forced to confront a question that cannot be avoided. Where does that computational process actually exist, if not in the space we still think is the foundation of everything? If you think this is just a strange, unexplained phenomenon, then there is someone who saw this issue very early on, David Deutsch at the University of Oxford, who in 1985 proposed the first model of a quantum computer as a real physical system, rather than just a mathematical concept. What makes his approach special is that he did not view quantum computation as a clever computational trick, but as a window into how reality operates at its deepest level. According to Deutsch, the power of quantum computation comes from the superposition of quantum states, meaning a system is not limited to a single state, but exists in multiple possibilities at once. With n qubits, you do not just have n bits of information, but a state space of size 2a's, and this grows exponentially so fast that with about 300 qubits, the number of states that can be represented already exceeds the number of atoms in the observable universe, roughly 10^90 compared to 10^80. This is no longer an ordinary large number, but a sign that we are working with a structure that cannot be squeezed into familiar physical intuition, something you cannot draw, cannot imagine in an intuitive sense, yet can be manipulated mathematically and experimentally. And Deutsch went one step further that many people find uncomfortable. He connected this to Hugh Everett's many worlds interpretation from 1957, in which each state in the superposition corresponds to a separate branch of reality. This is not just a metaphorical way of speaking, but a serious attempt to answer the question we raised earlier. If the calculation cannot reside in a single world, then perhaps it is not limited to a single world. If you accept this view, then a quantum computer does not try out each possibility sequentially in a single space, but exploits many branches of reality at the same time, as if it is borrowing resources from a larger structure that we do not directly observe. This is why some calculations can be performed with far fewer steps than any classical algorithm. Not because the machine is faster in the ordinary sense, but because it is not limited to the same structure of reality. However, this is also the point where the debate becomes fierce, because many physicists do not accept having to introduce countless parallel worlds just to explain a computational phenomenon, and they look for other interpretation, from Copenhagen to hidden variable models. But so far, no model has both maintained simplicity and fully matched the experimental data. And that brings us to a very uncomfortable but unavoidable position. If Deutsch is right, then a quantum computer is not just a tool, but a form of indirect experimental evidence that reality may have a multi-layered structure, where what you call the world is only a very small slice of a much larger system. And the calculations you think are happening inside a small machine on a lab bench may actually be spreading through a structure we have only just begun to touch. If you still feel that all of this sounds more like a bold interpretation than a scientific conclusion, then there is a very important shift that physics has made since the mid-20th century, and it is not based on speculation, but on measurable principles. In 1961, Rolf Landauer proposed an idea that seemed simple but was revolutionary. Information is not an abstract concept that exists independently of the physical world, but it has real energy costs. When you erase one bit of information, you are not just changing a logical symbol in memory, you are forcing the system to dissipate a minimum amount of energy equal to kT ln2, where K is Boltzmann's constant and T is the temperature of the system. This number is very small at everyday scales, but what matters is not its magnitude, but the fact that it exists as an unbreakable limit, similar to the speed of light in relativity. That means every operation on information, whether storing, copying, or erasing, is a real physical process governed by the laws of thermodynamics, not just an abstract logical operation. What makes this principle special is that it has been experimentally confirmed. Researchers at the École Normale Supérieure in Paris directly measured the energy produced when erasing one bit of information in a microscopic system, and the results match Landauer's prediction, turning a theoretical idea into an undeniable physical reality. Once you accept that, you are forced to change your perspective, because information is no longer something we use to describe the world, but is part of the world itself. When you change information, you are changing the physical state, and when you process information, you are performing a measurable physical process. From here, a profound consequence emerges in modern physics. Systems are no longer described primarily by objects, but by states, and these states are precisely how information is encoded in nature. A particle is not just a point of matter, but a set of possibilities described by a wave function, and its evolution over time is the transformation of information. If you look at it this way, then what you call matter may only be the manifestation of information organized according to a certain structure, where stable states create what we observe as particles, atoms, and objects. When you follow this logic far enough, the boundary between physics and information begins to blur, because thermodynamics talks about entropy, and entropy is a measure of information, while quantum mechanics describes the evolution of states, that is, the transformation of information over time. All of this converges on one unavoidable conclusion: information is not secondary but fundamental. And if information is physical, then a new question arises, directly linking to what we have said about quantum computers. If reality is built from information, and the laws of physics describe how that information changes, then reality itself may be a continuously operating information system, not a computer in the familiar sense, but a structure where every interaction, every state change is a step in an information processing process. In that case, a quantum computer is no longer a device standing inside reality, but a system designed to exploit the very rules that reality uses at its deepest level. And this is the point where everything returns to the original question. If a quantum computer performs a calculation that cannot be efficiently described in familiar physical space, then where is that calculation taking place? If information is physical, then it must exist somewhere. But if space is no longer the fundamental foundation, then where may no longer be the right question. Instead, perhaps the calculation is taking place within the very information structure of reality, a structure we have only just begun to recognize through principles like Landauer's. and through the phenomena that quantum mechanics forces us to accept. In modern physics, especially since quantum field theory became the foundation of the Standard Model in the second half of the 20th century, the concept of a particle is no longer viewed as small marbles existing independently in space. Instead, what we call electrons, photons, or quarks are actually local excitations of fundamental fields that extend throughout space, and that means the particle itself is not a fundamental object, but only a specific state of a deepest system. When you describe a system this way, you are no longer talking about the position of an object in the classical sense, but about the configuration of a field. That is, a set of values that can change across space and time, or in other words, a set of distinguishable states. This is precisely the point where physics begins to intersect naturally with information, because in information theory, a distinguishable state is the basic unit of information. When you say a system can be in state A or state B, you are saying that the system carries one bit of information, and when you extend this to more complex systems, you are describing reality as a vast space of possible states where each state corresponds to a specific configuration of information. This is not a metaphor, but a conclusion reinforced from many different directions in physics. In thermodynamics, entropy is not just a quantity measuring disorder, but from Ludwig Boltzmann's work at the end of the 19th century. It is understood as the logarithm of the number of microstates corresponding to a macrostate, meaning it measures the number of ways a system can be arranged at the microscopic level while still looking the same at the macroscopic level. When you interpret this in modern language, you realize that entropy is a measure of the amount of information you lack about the system. When you combine that idea with Claude Shannon's information theory from 1948, where entropy is defined as a quantity measuring the uncertainty of information, a remarkable convergence begins to appear. Entropy in physics and entropy in information theory are essentially the same concept, viewed from two different angles. This means that when you talk about energy, heat, or the evolution of a physical system, you are also talking about how information is distributed, encoded, and transformed over time. From this perspective, what you call matter begins to lose its foundational role. An atom is no longer a tiny piece of matter, but a stable structure of information within a quantum field. A molecule is a more complex configuration of that information, and a larger object is simply an extremely complex network of interacting information states, following rules we call the laws of physics. Even those laws, from Newton's classical mechanics to quantum mechanics, can be seen as rules describing how these states transition from one configuration to another over time, much like steps in an algorithm. When you look at it this way long enough, you begin to see that the universe no longer resembles a collection of objects existing in space, but rather a process that is occurring, a process in which information is continuously updated, propagated, and restructured. This also helps explain why, in many modern fields, from particle physics to cosmology, scientists increasingly speak of information as a fundamental quantity. Studies of black holes, for example, have led to what is called the information paradox, where the central question is no longer where the energy goes, but where the information goes when matter falls into a black hole. And that shows that even under the most extreme conditions in the universe, information cannot be ignored. When you put all these pieces together, a clearer picture begins to emerge. Reality is not a collection of independent objects, but a vast state space where each point corresponds to an information configuration. And the evolution of the universe is the movement through that state space. At that point, the conclusion becomes unavoidable. Instead of living in a material universe in the traditional sense, where particles move through space and interact with each other, perhaps we are living in an information processing system where matter is only the way information manifests at a certain level. What you see, touch, and experience may only be the interface of a much deeper process, a process that quantum computers have only just begun to exploit in a controlled way. And when you return to the original question about where quantum computation takes place, the answer begins to change once again, because if reality is information, then computation does not need to reside in space, but may itself be the way space and everything within it is created from the beginning. From that perspective, one of the first phenomena that forced us to abandon the idea of a fixed and clear reality was the result of the double-slit experiment, which began in 1801 with Thomas Young, when he showed that light behaves not only as individual particles, but also as a wave that can interfere with itself. This was already surprising enough in the context of classical physics, but the story became far more uncomfortable in the 20th century, when physicists began performing more sophisticated versions of this experiment with material particles like electrons. Experiments with single electrons confirm something unavoidable, even when you fire electrons one at a time through two slits, and ensure there is no interaction between them. The final pattern on the screen is still an interference pattern, as if each electron had passed through both slits at the same time and interfered with itself. This is not a metaphor, but the only way mathematics and experimental data allow us to describe the phenomenon. In the language of quantum mechanics, this is called quantum superposition, where a system does not exist in a single definite state, but in a combination of many states at once, each carrying its own probability amplitude. When you have not yet performed a measurement, the system does not choose any specific state, and all possibilities exist in parallel as components of the same wave function. This leads to a conclusion that our intuition always tries to avoid. Before observation, there is no single reality in the sense we are familiar with. An electron is not here or there in the way a marble sits on a table, but exists as a distribution of possibilities, spread across space, until a measurement forces the system to manifest a specific outcome. This completely breaks the binary logic that classical philosophy, from the time of Aristotle, has relied on, where a proposition can only be true or false, and an object can only be in one position at one time. In the quantum world, those boundaries become blurred, and reality is no longer a collection of clear events, but a structure where possibilities overlap until they interact with a measuring system. What is important here is not only the strangeness of the phenomenon, but the fact that it has been repeatedly confirmed in a series of experiments with ever-increasing precision, from photons to electrons and even larger molecules, showing that this is not an exception, but a fundamental feature of nature. When you combine this with what was said earlier about information and states, a new picture begins to form. If the state of a system is information, and if the system can exist in multiple states at once before measurement, then that information does not exist as a fixed value, but as a continuous spectrum of possibilities. This brings us to a conclusion that is not easy to accept but hard to deny. Reality is not a collection of fixed states waiting to be discovered, but a space of possibilities that is being selected through the process of interaction and measurement. What you observe is not the entire reality, but a specific slice of a much larger structure, where other possibilities still exist at the mathematical description level and can influence the final result through interference. At that point, the idea of a stable, definite world independent of the observer begins to become difficult to maintain. And instead, you must accept that at the most fundamental level, reality may not be what exists, but the set of what can happen, a spectrum of possibilities of which we only see a small part each time we perform a measurement. From the point where we have just seen that reality is no longer a definite state, but a spectrum of possibilities, the next step goes even further, because not only is the state of a system indeterminate, but the relationship between systems also does not follow the way we think about space. In 1935, Albert Einstein, along with Podolsky and Rosen, presented the EPR paradox, in which he described a phenomenon he called spooky action at a distance, expressing his discomfort with the idea that two systems could be linked without any signal traveling through the space between them. That phenomenon is now called quantum entanglement, and it is not a minor detail, but a fundamental feature of nature. When two particles become quantum entangled, their states are no longer independent, but must be described as a single system, even if you separate them by meters or thousands of kilometers. This means that if you measure one particle and obtain a specific result, the state of the other particle is determined instantly, regardless of how far apart they are. Classical intuition would lead you to think that some signal must be traveling, but both quantum mechanics and relativity forbid any information from moving faster than the speed of light. This is the real point of tension, where the two great foundations of physics seem to clash with our intuition. In 1964, John Bell proposed a theorem that allows this to be tested experimentally through Bell's inequality, showing that if the world operates according to local laws, then the correlations between two particles must lie within a certain limit. Quantum mechanics predicts that under some conditions that limit will be violated. In 1982, Alain Aspect conducted an experiment with entangled photon pairs and confirmed that Bell's inequality is indeed violated, which rules out models based on local hidden variables and forces us to accept that nature does not operate in a local way as we once thought. This does not mean that information travels instantaneously, but that our understanding of transmission and location may have been wrong from the beginning. No signal flies from one particle to the other, yet the results remain linked instantaneously, which shows that information about the system is not distributed in space in the classical way. When you try to ask where this state is located, that question begins to lose meaning, because the state of an entangled system cannot be assigned to each individual part, but only exists at the level of the entire system. In classical physics, you can always assign a location to an object, and all information about it can be traced back to that location. But in the quantum world, this is no longer true. An entangled system must be viewed as a unified entity spread out, where the parts have no independent meaning in terms of information. When you measure one part, you are interacting with the entire structure, and the result reflects that structure rather than just the part you measured. This shakes the concept of location in physics, because if information is not tied to a specific position, then space may not be the fundamental foundation. When combined with the phenomenon of superposition, a clearer picture emerges. Not only is the state of the system indeterminate before measurement, but the information about the system also does not reside at a specific point in space. Instead, it is distributed in a non-local way that we can only describe mathematically. This forces us to reconsider the role of space. Perhaps it is not what determines how reality operates at the fundamental level, but only an appearance that emerges when many information states interact in a certain way. In that case, concepts like here and there may only be the way we organize our experience, rather than true features of the world. The conclusion is not a definitive statement, but the direction the data is pointing. Reality may be non-local, and what we call position may not be a fundamental factor. This brings us back to the original question about the quantum computer, because if information is not bound by position, then the calculations it performs also do not need to take place in a specific location, but may spread across the very non-local structure of reality, a structure we have only just begun to understand through phenomena like quantum entanglement. In quantum mechanics, when you perform a measurement on a system, its superposition state seems to collapse into a specific value, a single result that you can record. Before the measurement, the system is described by a wave function containing many possibilities. After the measurement, you are left with only one of those possibilities. It sounds reasonable, almost obvious, but the problem lies in the fact that no one really knows what the mechanism of this process is. Since the 1920s, Niels Bohr and his colleagues proposed the Copenhagen interpretation, in which measurement is viewed as a boundary between the quantum world and the classical world, where the wave function chooses a specific outcome. However, this interpretation does not explain why that process occurs, but only describes that it occurs, and that creates a large gap in our understanding. There is no equation in standard quantum mechanics that says this is the moment when the wave function collapses, which makes the theory both extremely accurate in its predictions and incomplete in describing the nature of the process. To clarify this strangeness, in 1935, Erwin Schrödinger presented the famous thought experiment about a cat in a sealed box, along with a quantum mechanism that could trigger poison. According to the quantum description, before you open the box, the system exists in a superposition state between cat alive and cat dead, not because we do not know the outcome, but because the theory says both possibilities coexist until a measurement is made. When you open the box, you see only one single outcome, and it seems that the act of observation has forced the system to choose. This leads to a question that cannot be avoided. Does reality exist independently of the observer or not? In classical physics, the answer has always been yes. Everything exists and happens regardless of whether anyone is observing or not. But in quantum mechanics, you cannot assign a definite state to the system before measurement. The wave function only provides probabilities and does not affirm that a specific reality exists beforehand. This does not mean that human consciousness creates reality in a mystical sense, but it shows that the act of measurement, that is, the interaction between the system and the environment, or the measuring device, plays an inseparable role in determining the outcome. Some interpretations try to remove the special role of observation, such as the many worlds interpretation, where every possibility occurs and there is no collapse. But that leads to a picture that is even harder to accept. The important point is that the concept of objective begins to lose its foundation, because if you cannot say that a system has a specific state before measurement, then reality is no longer a collection of fixed properties that exist independently. Instead, it becomes a structure where possibilities exist in parallel, and a specific outcome only appears when there is an interaction strong enough to distinguish them. When you combine this with entanglement, where information does not reside at a specific location, you begin to see that not only where but also what is not determined beforehand in the classical way. Reality at the fundamental level may not be a complete picture waiting to be discovered, but a process in which possibilities are realized through interaction. The conclusion is not that we have a final answer, but that we are forced to change the way we ask questions. Because instead of asking what state the system is in before measurement, perhaps the right question is which possibilities exist and what determines the way they become a specific outcome. This brings us to a point very different from the original intuition. Reality may not be completely independent of the act of measurement, and what we observe is not a passive reflection of a pre-existing world, but the result of an interaction process between us and the deeper structure of nature. When you put all these pieces together, something begins to become clear in a way that is very hard to ignore. Quantum superposition, quantum entanglement, and the entire measurement problem are not just isolated strange phenomena, but signs that our classical intuition about reality is no longer working. In the familiar world, you always assume that an object has a definite state, that it exists in a specific location, and that every influence must propagate through space in a traceable way. These three quantum principles successively break each of those assumptions. Superposition says that a system does not have a definite state before measurement. Entanglement says that information is not limited to a specific location, and the measurement problem says that the very outcome you observe may depend on how you interact with the system. What is important is that these are not unverified theoretical speculations, but results that have been confirmed through hundreds of experiments over nearly a century. From the first works in the 1920s to modern experiments with extremely high precision using photons, electrons, ions, and even larger quantum systems. Each time we test it, nature gives the same answer, even when that answer contradicts everything our intuition expects. This creates a very special situation in science, where you have a theory that works almost perfectly in predicting outcomes, but cannot be interpreted using concepts that the human brain finds reasonable. You can write down the equations, calculate the probability amplitudes, and accurately predict what will happen in an experiment. But when you try to picture it in your mind, everything starts to fall apart. There is no visual image that corresponds to a system that is both here and there, or two systems far apart, yet behaving as one. This forces us to acknowledge something that physics rarely has to face at this level. There are aspects of reality that we can describe mathematically, but cannot visualize with intuition. Mathematics becomes the only precise language we have, while intuition, which was once a powerful tool in classical physics, now becomes a source of misunderstanding. What is important is not to misunderstand this as a failure of the theory. Quantum mechanics is not wrong. In fact, it is one of the most accurate theories ever developed, with predictions that match experiment at a level rarely achieved in any field. The problem lies in the fact that our brains evolved to handle the world at the human scale, where objects have clear positions, time flows in a single direction, and every interaction can be tracked in space. When you go down to the quantum level, those conditions no longer apply, and our intuition begins to fail. This is not surprising from an evolutionary perspective, but it has a profound consequence. What you feel is obvious may be completely unrelated to the way reality actually operates. When you accept this, the story begins to move into a different stage. Instead of trying to force quantum mechanics into the framework of classical intuition, you begin to consider the possibility that the framework itself needs to be replaced. If the state is indeterminate before measurement, If information has no specific location, and if the outcome depends on interaction, then concepts like object, position, and state may only be effective models, ways in which we simplify a much more complex reality. This does not mean the world becomes random or meaningless, but on the contrary, it may be described more accurately by abstract mathematical structures, where the rules remain very clear, but no longer correspond directly to the images we are familiar with. This is also the point where what we have said about information begins to connect again. If reality is an information structure, and if that information is not bound by space or definite states, then our inability to visualize it is not unusual. You cannot see a state space with millions of dimensions, just as you cannot visualize a wave function spread across many possibilities at once. But you can describe it, manipulate it, and test its predictions. And that is exactly what modern physics is doing. All of this leads to a very specific feeling. The foundation we once trusted begins to shake, not because science has failed, but because it has succeeded too well in showing that our initial assumptions are insufficient. The question is no longer how to explain an individual phenomenon, but how to build a completely new understanding of reality that does not rely on the old intuitions. And if you think this is already the most difficult point, then the story does not stop here, because when we bring these principles into a system that can perform computation, the consequences become much more powerful. Going further in that direction, an even more fundamental change begins to emerge, because not only is our intuition about states and interactions broken, but the very concept of space also begins to lose its foundational role. In classical physics, everything takes place in a familiar three-dimensional space, where each object has a definite position and all information about it can be attached to that position. But in quantum mechanics, the state of a system is not described directly in this three-dimensional space, but in an abstract mathematical structure called Hilbert space. This space does not resemble anything you can directly imagine, because its number of dimensions is not 3, but can be dozens, millions, or even infinite, depending on the system you are considering. Each point in Hilbert space corresponds to a possible state of the system, and the evolution of the system over time is described as a trajectory in that space, rather than as a simple motion in physical space. What is important is that Hilbert space is not the place where the system exists in the ordinary sense, but a way of encoding all information about the system in a mathematical structure. This leads to a very uncomfortable but unavoidable consequence. If the true state of a system is described in a space with an extremely large or infinite number of dimensions, then the three-dimensional space we experience may not be the fundamental foundation of reality, but only an effective manifestation, a way in which a small part of that structure is projected so that we can perceive it. When you work with a quantum system consisting of many particles, the number of dimensions of Hilbert space increases exponentially with the number of particles, which means the full description of the system quickly becomes impossible to represent in any familiar physical space. This is not just a technical problem in computation, but a sign that the very structure of reality may not fit the way we organize it in three-dimensional space. When you combine this with what we have seen about superposition and entanglement, the picture becomes clearer. A quantum state does not reside at a specific position because it is not defined in physical space in the way a classical object is defined. The information about the system is distributed throughout the entire state space, and assigning a specific position to it is only an approximation that appears when you perform a measurement. In the case of entanglement, you cannot even separate the system's information into parts corresponding to each individual position, because the state of the entire system is an indivisible entity. This reinforces the idea that quantum information has no definite position in the ordinary sense. At that point, a seemingly very basic question begins to become difficult to answer. Where? If the state of the system does not lie in three-dimensional space, if information is not tied to a specific position, then asking where a process occurs may no longer be a valid question. This is not because we lack information, but because the concept of where may only have meaning in an effective description at large scales, where quantum states have interacted with the environment and produced outcomes that we can assign to specific positions. At the fundamental level, where states still exist in Hilbert space, that question may simply not apply. This forces us to reconsider the role of space in physics, rather than being the foundation on which everything exists. Space may be a structure that emerges from a deeper description, where information and states are the fundamental elements. Some modern directions in theoretical physics, such as in quantum gravity, even propose that space and time may emerge, that is, appear from information relationships between parts of the system, rather than existing as independent entities. In that case, what you experience as distance, position, and motion may only be the way a complex information structure is manifested at the scale you can observe. The conclusion is not that we have clearly understood this mechanism, but that we are being forced to change the way we ask questions. If information does not reside in space, if states are described in an abstract space with a very large number of dimensions, and then trying to force everything into the familiar three-dimensional framework may be the reason everything feels absurd. In that case, instead of asking where a system is, perhaps the more appropriate question is how its state is organized in information space, and how that structure relates to what we observe as physical space. And if this is correct, then the space you're experiencing right now may not be the foundation of reality, but only a surface layer, a way in which a much deeper structure is manifested so that you can interact with it. A deeper ship begins to emerge. Because if space is no longer the absolute foundation and states are not tied to specific locations, then reality may not be a collection of objects existing independently, but a continuous process of state change. In classical physics, you are used to thinking of the world as stable objects, a rock, a planet, a body, all existing as stable entities moving through space and changing over time. But when you step into modern physics, especially quantum mechanics, that description begins to lose its fundamental character. Instead of talking about objects, you talk about the state of a system, and that state is not something static, but a continuously changing structure. Each quantum system is described by a wave function, a mathematical object that contains all the information that can be known about the system. And what is important is that this wave function does not stand still. It evolves over time according to a definite law, described by the equation Erwin Schrödinger proposed in 1926. This equation does not describe the motion of an object in space, but rather the way the entire state of the system changes in an abstract space, where all possibilities are encoded and transformed over time. When you observe how the wave function evolves, you begin to see a parallel with an algorithm. There is an initial state, there is a definite rule, and there is a sequence of subsequent states generated from that rule, repeating continuously. There is no object that needs to exist as a fixed entity in this process, but only an information structure that is being constantly updated. This is not a metaphorical comparison, but the way the mathematics of quantum mechanics actually operates. Where solving the equation is not about tracking a particle moving from one point to another, but about tracking the transformation of the entire probability distribution, that is, the entire information structure of the system. That means what you call objects may only be stable patterns that appear in this evolutionary process, like repeating structures in a data stream, rather than fundamental entities that exist independently. When you place this alongside what we have seen about superposition, entanglement, and measurement, everything begins to connect into a coherent picture. The state is indeterminate before measurement. Information has no specific location, and the outcome depends on interaction, all of which fit with the idea that reality is a dynamic process, where possibilities continuously transform and only occasionally manifest as a specific outcome when there is a sufficiently strong interaction. What you observe as an object or a state is only a temporary slice in that process, a moment when the information structure reaches a form stable enough for you to recognize. Before and after that moment, the system continues to evolve, and there is no point where you can say that this is the single, true state of it in an absolute sense. This also explains why trying to assign a fixed essence to objects in the quantum world always leads to contradictions, because if reality is a process, then asking what a system is at a specific moment may not be the right question. The more appropriate question is, how is the system transforming? This is a very large change in the way we understand the world, because it replaces a static picture with a dynamic one, where existence is not a state, but a continuous process. In this picture, the laws of physics are no longer rules that control objects, but rules that describe how information is transformed over time. And when you follow that logic to its end, the conclusion begins to become clear. Reality may not be a thing that exists independently, but a continuous information processing process, where everything you observe is the result of the evolution of states according to certain rules, and what you call matter, space, or time may only be features that emerge from that process, like patterns that appear from a complex computational system, a system that quantum computers have only just begun to touch at a very primitive level. If you look at everything in that direction, then a quantum computer is no longer a strange tool outside the story, but the place where all these ideas converge into a system that can function in the real world. Its basic concept, the qubit, was proposed in the 1980s in the works of physicists like David Deutsch, when they realized that if nature operates according to quantum mechanics, then efficiently simulating nature must also be based on those same principles. However, it was only with the development of cooling technology, control, and isolation of quantum systems from the environment that this concept began to be realized in laboratories around the world. The core difference is that a qubit is not like a classical bit that can only be in state 0 or 1, but can exist in a superposition state of both 0 and 1 at the same time, with definite probability amplitudes. This is not a mathematical trick, but a physical property that has been verified, and when you combine multiple qubits together, you are not just increasing the number of bits. You are expanding the state space of the system exponentially. A system consisting of n qubits can represent two n states simultaneously, and that quickly surpasses any direct representation capability of classical computers. For example, Google's 53-qubit system in 2019 could represent up to 253 states, equivalent to thousands of trillions of different configurations, a number that you cannot store or process sequentially with any classical architecture. But what is important is not the number, but the way the system uses that state space. A quantum computer does not go through each state sequentially. Instead, it lets the entire system evolve in this state space according to the rules of quantum mechanics, where probability amplitudes can interfere with each other. By designing sequences of quantum operations, also known as quantum gates, one can amplify the probability of correct outcomes and suppress incorrect ones, causing the entire system to compute in a way that has no direct equivalent in the classical world. To achieve this, the system must take advantage of precisely the phenomena that we previously viewed as paradoxes, specifically quantum superposition and quantum entanglement. Superposition allows a system to exist in many states at once, while entanglement links the qubits into a structure where information no longer resides in individual parts, but in the relationships between them. What is remarkable is that a quantum computer does not try to avoid these phenomena. It depends entirely on them to function. If you remove superposition, the system reverts to a classical computer. If you remove entanglement, you lose most of the computational advantage. That means what we once saw as problems in understanding quantum mechanics are actually resources that a machine can exploit. This is the point where the story shifts clearly from theory to reality. We are not just talking about abstract equations, but building devices that operate based on those very rules. And when a device can function stably, repeatedly, and produce measurable results based on such principles, you can no longer treat them as mere strange hypotheses. This leads to a very hard-to-avoid conclusion. A quantum computer is not just a faster computational tool, but a system designed to directly exploit the deeper structure of reality. It does not simulate physical laws from the outside. It operates right inside them, using precisely the features we cannot visualize to perform calculations that the classical world cannot handle efficiently. And if a machine can do that, then the question is no longer why it is faster, but what part of reality it is interacting with that we do not yet truly understand, because what it exploits is not a minor detail, but may be the very foundation of how the universe operates. From the way a quantum computer works, a question begins to appear that at first sounds simple, but leads straight to the heart of the matter. Where is that computation actually taking place? In a classical computer, you can always point to a specific location on the chip, where transistors switch on and off, where bits are stored and processed, and the entire computational process can be traced back to local physical changes in space. But with a quantum computer, this description begins to collapse. You can point to a system of physical qubits, whether trapped ions, superconducting circuits, or photons, but the full state of the system does not fit neatly into any part of that physical structure. As we have seen, a system of n qubits is described by a state in Hilbert space with 2n dimensions, and that means the information about the system cannot be stored in a local way like bits in classical memory. There is no memory cell that contains this state, no region on the chip where you can point and say the entire calculation is happening there. Instead, the state of the system is distributed across the entire structure, and more importantly, across the entire abstract state space we use to describe it. This leads to a fundamental change in the understanding of computation in a quantum computer. Computation is not a sequence of local steps performed one after another, but the evolution of the entire system in state space. When you apply a quantum gate, you are not just changing a small part of the system, you are transforming the entire state, adjusting the probability amplitudes of all possibilities at once. This means computation does not run through positions in space like an electrical signal running through a circuit, but spreads in an abstract structure where all states are linked together. When the system evolves, it does not move from point A to point B in physical space, but moves in Hilbert space, a space you cannot draw, cannot visualize, but which contains all the information about the system. When you try to trace the entire process back to a specific location, you begin to see that the concept no longer applies. There is no point where the computation resides, because the computation itself is the transformation of a structure that has no position in the classical sense. This becomes even clearer when you consider entanglement. When qubits are entangled with each other, their states cannot be separated into independent parts, and the information about the system exists only at the level of the entire structure. That means there is no way to say that one part of the computation happens here and another part happens there, because the entire computation is an indivisible entity according to space. From here, the question begins to become deeper and also more uncomfortable. If the computation does not reside at a specific location in physical space, then where is it taking place? Some interpretations, such as the one proposed by David Deutsch, suggest that computation may spread across multiple branches of reality, meaning it is not limited to a single world. Other interpretations try to keep everything within a single universe, but must accept that information is encoded in a non-local way that cannot be traced to specific locations. Whichever way you choose, you must abandon the idea that computation is a process occurring at a point in space, in the familiar sense. This is not just a technical detail, but a foundational issue in quantum computing. Because if you cannot determine where the computation takes place, then you must also rethink the question of how resources are used. In a classical computer, you can count the number of transistors, the number of operations, the energy consumed at each location. But in a quantum computer, the primary resource is the structure of the state space, something that has no direct representation in physical space. This explains why quantum computers can handle problems that classical machines cannot, not because they are faster in the traditional sense, but because they exploit a structure that classical machines cannot access. The conclusion is not that we have a clear answer, but that we have reached a point where the original question needs to be changed. Instead of asking where the computation takes place, perhaps the right question is how the computation is represented in state space and how that structure relates to the physical world we observe. And this is the biggest issue in quantum computing. Not building a more stable machine or reducing errors, but understanding the nature of the process that the machine is exploiting. Because when you cannot point to where the computation takes place, you begin to suspect that the very concept of location may no longer be the foundation of reality. You realize that quantum computation does not reside at any location in space in the familiar sense. And a new way of looking begins to form, one that completely changes how we understand this very machine. Because a quantum computer no longer resembles a device that simulates reality from the outside, but a system that directly interacts with the deepest rules of reality. In a classical computer, every computation is a modeling process. You build a representation of the problem in bits. You manipulate those bits according to logical rules, and the result is only a reflection of how you encoded the problem. But in a quantum computer, you are not only simulating quantum systems, you are actually using quantum systems to perform the computation, which means the computational process itself occurs according to the exact laws that nature uses at the fundamental level. When you design a quantum algorithm, you are not imposing a rule from the outside on the system, but arranging interactions so that the system evolves in a way that produces the desired result. This is a very profound difference because it turns computation from an abstract process into a direct physical process. This also explains why quantum computers can do things that classical machines cannot. Their power does not come from running faster within the same framework, but from operating within a different framework. A framework where superposition allows many possibilities to exist simultaneously. Entanglement links parts of the system into an inseparable structure, and the evolution of the wave function exploits interference to select the appropriate outcome. These are not additional features, but fundamental characteristics of the way reality operates at the quantum level. When you build a quantum computer, you are creating a system that can directly exploit those characteristics, rather than trying to simulate them with classical means. This is similar to the difference between simulating the flow of water with equations and actually using flowing water to perform a task, except that in this case, the flow is the evolution of the quantum state in an abstract space. From this perspective, the inability to simulate a quantum computer with classical machines is no longer a mystery. Classical machines are limited by the way they represent information, with bits having definite states and local operations in physical space. To simulate a quantum system with n qubits, you need to track 2n probability amplitudes, and this number grows too fast to be handled directly. But the problem is not only the number of variables, but the structure of the state space itself. A classical machine tries to squeeze a structure with an extremely large number of dimensions into a system designed for local states, and that leads to an explosion of resources. A quantum computer does not face that problem because it does not try to represent that structure from the outside, but operates directly inside it. In other words, it does not describe the state space. It lives in that space. This brings us to a conclusion that is hard to avoid, but also very powerful. If a machine can operate by directly exploiting the basic rules of quantum mechanics, and if those rules describe how information is organized and transformed at the deepest level of nature, then a quantum computer is not just a technological tool, but a form of interface with the foundational layer of reality. When you run a quantum algorithm, you are not only performing a calculation, but activating a process within the very information structure of the universe, a process that we can only describe mathematically, but now can control and exploit to a certain degree. This also explains why the questions we have raised, where the computation takes place, where the information resides, whether the state exists before measurement or not, are no longer peripheral questions, but have become central to the entire issue. Because when you build a machine based on these principles, you are not only confronting them theoretically, but handling them in practice. And each time the machine works as predicted, each time you measure a result that matches the theory, you are receiving confirmation that those strange rules do not just exist on paper, but are the way reality actually operates. When viewed this way, a quantum computer is not just a step forward in technology, but a step forward in perception. It forces us to accept that what we once considered intuition may not apply at the fundamental level, and that reality may be built from principles we have only just begun to understand. And if that is correct, then the fact that we can build and operate such machines means we are touching the foundational layer of reality, not through speculation, but through direct interaction with it, one calculation at a time. A quantum computer is directly exploiting the deepest rules of reality, and an unavoidable issue emerges, because if we are truly touching that foundational layer, then we must understand how it operates. But reality shows the opposite. We can use quantum mechanics with extraordinary precision while still not agreeing on what it really means. One of the oldest interpretations is the Copenhagen interpretation, associated with Niels Bohr, in which the quantum state is described by a wave function, and measurement causes that wave function to collapse into a specific outcome. But the problem is that this interpretation does not provide a clear mechanism for that collapse. It does not say when this process occurs, what triggers it, or why one specific outcome is chosen instead of the other possibilities. And this makes it resemble a pragmatic rule more than a complete description of reality. You can use it to calculate, to predict. But when you ask what is really happening in the measurement process, you only get a vague answer that this is where classical and quantum theory meet, a boundary that no one can define precisely. The dissatisfaction has led to efforts to find other explanations, among which the most prominent is the many worlds interpretation proposed by Hugh Everett in 1957. Instead of assuming that the wave function collapses, Everett proposed that the wave function never collapses, but all possibilities continue to exist, each possibility corresponding to a branch of reality. When you perform a measurement, you do not choose an outcome, but you become part of a specific branch in which that outcome occurs, while the other branches continue to exist with different outcomes. This interpretation has an important advantage. It eliminates the need to explain the mechanism of collapse, because no collapse occurs. However, it also comes at a very high cost, which is the existence of countless parallel realities that cannot be directly observed. Many physicists feel that this makes the theory too expensive ontologically, because you have to accept an infinite number of worlds just to explain a phenomenon that you previously thought required only a single world. Another direction tries to preserve classical intuition by assuming that there are unknown hidden variables that determine the outcome of measurements, meaning quantum systems actually have definite states, but we do not have enough information to describe them. However, this direction ran into a major obstacle with the work of John Bell in 1964, when he proved that any hidden variable theory obeying the principle of locality cannot reproduce the predictions of quantum mechanics. Subsequent experiments, especially those that violate Bell's inequality, confirmed that local hidden variable models are incompatible with reality, forcing physicists to abandon one of two assumptions, either locality or predetermined reality. Some non-local hidden variable models still exist, but they are often complex and do not provide a clearer picture than standard quantum mechanics. When you look at the entire picture, one thing becomes clear. There is no interpretation that is fully accepted. Each one solves some problems but creates others. Copenhagen is simple, but does not explain the nature of collapse. Many worlds eliminates collapse, but introduces countless unobservable realities. Hidden variables try to restore classical intuition, but are limited by experimental results related to John Bell's work. This creates a very special situation in science, where a theory works extremely well in terms of prediction, but lacks a conceptual foundation that everyone agrees on. You can use quantum mechanics to design transistors, lasers, and now quantum computers. But when you ask what is really happening, the answer depends on the interpretation you choose, and none of them has been proven correct. This does not mean physics has failed, but on the contrary, it shows that we are at the boundary of understanding. The history of science has gone through similar stages many times, where mathematical tools precede conceptual understanding, and it takes time to develop a more complete theoretical framework. However, in the case of quantum mechanics, the gap between predictive power and understanding seems deeper than at any previous time. When you combine this with the fact that quantum computers are directly exploiting these principles to perform calculations that classical machines cannot, you begin to see that the problem is no longer just philosophical but has real consequences. We are building machines based on a theory that we do not fully understand, and each time those machines work correctly, we confirm that the theory is accurate. But at the same time, we are reminded that we still do not have a complete story about reality. The conclusion is not that we have a wrong answer, but that we do not yet have a complete answer. Quantum mechanics, with all its successes, may still be only a part of a deeper theory that we have not yet discovered. The paradoxes we encounter may not be signs of contradiction, but signs that we are using a language that is not yet sufficient to describe a much more complex structure. And as quantum computers continue to develop, they not only open up new technological possibilities, but also force us to face the reality that our understanding of the foundations of the universe is still incomplete, and may still be very far from complete. Putting that entire picture together, a very clear feeling begins to emerge. We do not have a unified answer about the nature of reality, even though we have a theory that works almost perfectly in terms of prediction. Each interpretation we have just gone through tries to fill this gap but none does so without creating new problems. The Copenhagen interpretation accepts the collapse of the wave function but does not explain the mechanism. Hugh Everett, with many worlds, eliminates collapse, but introduces countless parallel realities, and hidden variable models are severely limited by experimental results related to John Bell's work. This leads to a situation where you have many models, but none is complete, each carrying a hole that you cannot ignore. And what is important is that these holes are not minor details that can be fixed with a few technical adjustments, but problems that lie at the very foundation of the way we understand the world. In previous stages of the history of science, when a theory ran into problems, there was usually a clear path. You could go back to an older, simpler model and start over from there. But in this case, that path no longer exists. You cannot go back to classical physics because every experiment over nearly a century has confirmed that quantum mechanics is correct at the fundamental level. You cannot say that an electron is really a particle with a definite position that we have not yet measured, because experiments have shown that this does not fit the data. You also cannot ignore entanglement or superposition, because they are not exceptions but core features of nature. This means we are stuck in a situation where the current theory is undeniable experimentally, but cannot be fully interpreted using the concepts we have. This is the point where the problem shifts from technology to perception. Quantum computers, as we have seen, do not create these paradoxes. They only make them impossible to ignore. When a machine actually works based on superposition, entanglement, and the evolution of the wave function, you can no longer treat those phenomena as theoretical curiosities. They become real factors you must face, things that determine whether the machine works or not. But at the same time, the fact that the machine works does not help you understand the nature of those phenomena any better. You can build a quantum computer, improve its accuracy, reduce errors, and perform increasingly complex calculations, but the question, what is really happening, remains unresolved. This creates a paradox in the very way we do science. We often think that when a theory is confirmed many times, we get closer to understanding it. But in this case, each new confirmation only highlights the gap between prediction and understanding. We know how to use quantum mechanics better than ever, but that does not mean we understand it better. In fact, it could be said that we are increasingly realizing that we do not understand it in an intuitive sense. This leads to an uncomfortable conclusion. We are in a crisis of perception, not a crisis of data or technology, but a crisis of the way we imagine reality. The concepts we rely on, objects, position, state, causality, all begin to lose their universality when applied at the fundamental level. And while they still work well at large scales, where our intuition was formed, they are no longer sufficient to describe what is happening at the quantum level. When you take this seriously, you begin to see that the problem is not that we lack data, but that we lack an appropriate conceptual framework. Perhaps a completely new way of thinking is needed, a new language to describe reality, just as quantum mechanics replaced classical mechanics in describing the microscopic world. But until that happens, we must accept a very strange reality. We are living in a universe that we can predict with extremely high accuracy, but cannot fully explain according to the standards we once set. And that is the very nature of this crisis. Not that we do not know what will happen, but that we do not really know what exists. In 1905, Albert Einstein proposed special relativity and established an absolute limit. No signal can travel faster than the speed of light. This was not just a technical number, but a structural boundary of reality, forcing us to abandon intuitive ideas about space and time as absolute foundations and instead accept that they depend on the reference frame. At first, this also caused strong resistance because it contradicted intuition built from everyday experience. But over time, it became an indispensable part of the way we understand the universe. However, the limit we are facing now has a different nature. It is not a limit on speed or energy, but a limit on the ability to understand. We are not forbidden from observing or measuring quantum phenomena. On the contrary, we can measure them with extremely high precision and predict the results reliably. But what we cannot do fully is attach an intuitive meaning to those phenomena, a conceptual story that the human brain can grasp naturally. This leads to a very clear separation between two aspects of science, description, and understanding, modern science, especially in physics, has reached a level where the ability to describe mathematically far exceeds the ability to understand in the ordinary sense. You can write equations describing the evolution of a quantum system. You can calculate probabilities and test them with experiments. But when you try to turn those equations into a visual image, you quickly realize that no image fits. This is not a failure, but a sign that we are working with aspects of reality that go beyond what human intuition was designed to handle. In the history of science, this has happened before. When Isaac Newton introduced the concept of gravitational force acting at a distance, many people also felt uncomfortable with the idea that two objects could influence each other without a clear intermediate mechanism. When electromagnetism developed in the 19th century, concepts like fields and waves also initially lacked clear intuition. In each case, science moved forward by accepting precise mathematical descriptions, even when their intuitive meaning was not yet fully clear. The difference in the current case is the extent to which the gap between description and understanding has widened. With quantum mechanics, we not only lack a complete visual image, but we also have multiple competing interpretations, each consistent with the data but leading to different pictures of reality. This makes saying that we understand the theory much more complicated. It may be more accurate to say that we know how to use it, know how to predict and test, but do not yet have a single conceptual story that everyone accepts. And that is not a temporary failure, but may be a feature of the way science works when approaching the deepest layers of nature. From this perspective, the current situation is not a dead end, but a boundary. It marks the point where our current tools, both mathematical and conceptual, are being pushed to their limits. We can continue to expand those tools, develop new theories, or find deeper interpretations, but at this moment we must accept that there are questions without clear answers. What is important is to recognize that this is a normal part of the scientific process. Every time we reach such a boundary, it not only shows what we do not yet know, but also points to the direction in which understanding may develop in the future. The conclusion is not that science has failed, but that we are exactly where science should be, at the boundary between the known and the unknown. This is the point where questions become deepest, where the most basic assumptions are questioned, and where the greatest breakthroughs can occur. And in the context of quantum mechanics and quantum computing, that boundary is the nature of reality itself, something we can describe with astonishing accuracy, but are still learning how to understand. For most of history, we have viewed reality as a collection of objects existing independently, interacting in space and time. But quantum mechanics, together with what we have seen about information and computation, is forcing us to reconsider that assumption. Perhaps reality is not matter in the traditional sense, not things that can be pointed to and exist independently, but a deeper structure of which matter is only the surface manifestation. One of the possibilities being seriously considered is that reality is fundamentally information, where everything we observe is only the way information is organized and transformed over time. This idea does not come only from information theory, but is also reinforced by results in quantum mechanics, thermodynamics, and even black hole research, where information seems to play a more fundamental role than matter. Another possibility, related but going further, is that reality may be fundamentally mathematical. In this view, mathematical structures are not just tools we use to describe the world, but the world itself. Equations do not merely describe how things work, but are the way things exist. This may sound extreme, but it explains why mathematics can describe nature with astonishing accuracy, to the point that many physicists have called it the unreasonable effectiveness of mathematics. If reality is truly a mathematical structure, then our ability to describe it mathematically is not surprising but inevitable. However, this view also raises difficult questions. If reality is mathematics, then what is the relationship between mathematics and our experience? And why can an abstract structure lead to a world we can perceive? What is noteworthy is that these questions no longer belong solely to philosophy in the traditional sense, but are appearing right at the center of modern physics. When you try to understand quantum mechanics, you cannot avoid confronting issues about the nature of reality, about the role of observation, and about how information is organized. When you build a quantum computer, You are not just doing engineering, but interacting with principles that raise profound philosophical questions. This creates a rare convergence between physics and philosophy, where questions once considered abstract now become issues that can be tested indirectly through experiments and technology. However, this convergence does not mean we are close to having answers. In fact, it may show that the questions are far more complex than we once thought. Each view reality as matter, as information, or as mathematics provides a useful perspective, but none is complete. Perhaps reality is not entirely any of those, but something for which we do not yet have language to describe. Or it may be that each view is only one layer of description of the same deeper structure, just as wave and particle are two different ways of describing the same quantum phenomenon. When you reach this point, you begin to realize that the question, what is reality, may not have a simple answer or even a single answer. It may be a question that each generation must continue to explore, expand, and redefine as our understanding develops. This does not make the question less important, but on the contrary, makes it one of the central questions of science and philosophy. And perhaps the most important thing is to accept that not having an answer is not a failure, but a natural part of the process of inquiry. A sign that we are still on the journey of discovering the nature of the universe. A journey in which each step forward opens more questions than answers. In the 20th century, Gerard Hooft and later Leonard Susskind developed what is called the holographic principle, an idea originating from black hole research. According to this principle, all the information contained in a three-dimensional region of space can be encoded on the two-dimensional surface surrounding it, like a three-dimensional image stored on a flat hologram. This is not just a visual comparison, but a conclusion supported by calculations related to the entropy of black holes, where it was found that the maximum amount of information a region of space can hold is proportional to the area of its surface rather than its volume. If this is true at the fundamental level, then the three-dimensional space we experience may not be the foundational structure, but an emergent manifestation from an information description lying on a surface with fewer dimensions. This idea connects remarkably with what we have said about information in Hilbert space, because it suggests that information does not need to reside in space in the intuitive way, but can be encoded in ways completely different from our experience. When you combine this with phenomena like entanglement, where information has no local position, the picture begins to become more consistent. Perhaps space is only a way in which information is organized so that we can perceive it, rather than the ultimate foundation of reality. Some modern lines of research even propose that the structure of space and the distance between points may be determined by the degree of quantum entanglement between parts of the system, meaning information not only exists in space but may create space itself. From here, another idea, controversial but impossible to ignore, begins to appear in discussions about the nature of reality, the simulation hypothesis. In 2003, Nick Bostrom presented an argument based on logic and probability, suggesting that if a sufficiently advanced civilization can simulate universes with high detail, then the possibility that we are living in a simulation may not be small. What is important here is not to assert that we are definitely in a simulation, but to argue that this hypothesis does not contradict what we know about physics, especially when you view reality as an information system. If everything can be described by states and transformation rules, then in principle, a sufficiently complex system could recreate those states. What makes this hypothesis noteworthy is that it does not come only from philosophy, but has points of contact with ideas in modern physics. If space can be an emergent manifestation, if information can be encoded on structures with fewer dimensions, and if quantum systems can perform calculations that cannot be assigned to a specific location, then the idea that the reality we experience is not the most fundamental layer is no longer too strange. However, it must be emphasized that these ideas are still at the hypothetical level, and there is no direct evidence that we are actually living in a simulation. They are logical consequences of pushing current principles to their limits, rather than confirmed conclusions. When you place the holographic principle and the simulation hypothesis side by side, a common message begins to emerge. Reality may not be like what we experience directly. What you see, touch, and measure may be a layer of manifestation of a deeper structure where information is organized in ways we have only just begun to understand. This does not make the world unreal, but on the contrary, makes it far more complex and interesting than the initial imagination. And just as has happened many times in the history of science, realizing that our intuition does not fully reflect reality is not the end point, but the starting point of a deeper understanding of the universe we live in. Once you connect all those pieces together, from information being physical, states existing in Hilbert space, entanglement breaking locality, to the idea that space may only be a layer of manifestation of possibility, begins to appear with increasing clarity. Reality may not be a place containing objects, but a vast information processing system that is continuously operating. In this view, everything you observe is not static objects, but the result of information states being updated according to definite rules, much like the way a program evolves through computational steps. This is not a simple metaphor to make things easier to understand, but a serious interpretation that arises directly from the structure of modern physical laws. When you look at quantum mechanics, you do not see particles moving like marbles, but wave functions evolving. When you look at thermodynamics, you do not see heat as a substance, but entropy as a measure of information. When you look at gravity at a deeper level, you begin to see connections between geometry and information. All of this points in the same direction. Reality may be best understood as an information processing process. Within that framework, every physical interaction can be viewed as a computational step. When two particles interact, their states change according to a definite rule. When a system evolves according to the Schrödinger equation, it is performing a transformation on its information structure. When you perform a measurement, you are forcing the system to select one of the possible outcomes, that is, performing a selection step in state space. These processes do not require a central processor, do not require a computer in the traditional sense, because the very structure of the physical laws already plays the role of the algorithm. This leads to a completely different way of looking at the universe, not as a collection of objects obeying laws, but as a system in which the laws themselves are the rules for processing information. And the universe runs according to those rules. In this context, a quantum computer is no longer a special device lying outside reality, but a small part of that very system, a structure designed to exploit the information processing rules at the fundamental level. When you operate a quantum computer, you are not creating a new type of computation separate from nature, but taking advantage of the same mechanism that nature uses to evolve its own states. This explains why quantum computers can do things that classical machines cannot. They are not limited by the classical way of representing information, but operate directly in the state space that reality uses. In other words, they do not simulate reality, but participate in the same process that reality is carrying out. This leads to an idea that is both simple and profound. When you observe a quantum computer working, you are not just looking at a computing machine, but at a part of reality, performing its own computation in a controllable way. What you see on the screen, the measured results, are only the final part of a process that has taken place in a deeper structure, where states have interfered, combined, and evolved according to rules we have only just begun to understand. And this is not only true for quantum computers, but may be true for the entire universe. Every interaction, every event, every physical process may be a step in a vast computation that is taking place, a process that has no clear beginning or end, but only the continuous evolution of information. What is important is that this view does not require you to assume a computer in the ordinary sense standing behind the universe. There is no CPU, no separate memory, no operator. Instead, the physical laws themselves play the role of the algorithm, and the state of the universe at each moment is the data being processed. This is a view compatible with what we already know, but at the same time it opens up a completely new understanding of the nature of reality. It explains why mathematics can describe nature so accurately, because if reality is a computational process, then mathematics is not just a descriptive tool, but the language of the process itself. When you accept this possibility, many previous questions begin to connect with each other. Why does information play a fundamental role? Why do quantum states exist in a space with a very large number of dimensions? Why does entanglement allow non-local correlations? All of these may be manifestations of a deeper information structure, where concepts like space and matter are only the ways that computational process manifests at a certain level. This does not mean we have a complete theory, but indicates that this direction may be one of the most consistent ways to connect the pieces we have gathered. The conclusion is not a definitive statement that the universe is a computer, but an acknowledgement that this is a serious possibility in modern physics, a possibility supported by many different lines of evidence, from quantum mechanics to information theory and research on space-time. And if that is correct, then what we are doing when studying physics, when building quantum computers, when asking questions about reality, is not only observing the universe from the outside, but gradually understanding the way the universe is computing itself step by step, returning to the original question about the quantum computer, which at first seemed like just a technological advance, now looks like a door opening to a much deeper issue. What are we really seeing when such a machine operates? We have gone from the simple bits of classical computers, through qubits existing in superposition, through entanglement breaking the idea of location, through measurement shaking the concept of objective reality, and finally touching the possibility that the universe itself may be operating as an information processing system. But after all those steps, one thing remains unchanged. We still do not have a final answer. There is no single theory that everyone agrees on to explain what is really happening behind the equations. There is no interpretation that can solve every problem without creating new questions, and that is not a sign of failure, but a sign that we are exactly where science always finds itself when touching the deepest questions. If you look at history, science has never advanced by waiting until there is a perfect answer before continuing. It advances by accepting that there are things we do not yet understand, but still continuing to ask questions, still continuing to experiment, still continuing to build better models. In this context, that becomes clearer than ever. We can build quantum computers. We can predict the results of experiments with extremely high accuracy, but when we are asked, what does this mean? The most honest answer is still, we do not know. This requires a type of intellectual honesty that is not always easy to accept. There's a very strong temptation to choose one interpretation, Copenhagen, many worlds or any other model, and say that it is the final answer, simply because it gives a sense of completeness. But science does not work that way. It does not reward baseless certainty, but rewards the ability to keep multiple possibilities open at the same time, just like the way a quantum state exists in many possibilities before measurement. Intellectual honesty means acknowledging that we may be wrong, that current concepts may not be sufficient, and that reality may be far different from what we expect. When you look at it this way, the story of the quantum computer is no longer just a story of a new technology, but a test of the way we understand the world. It forces us to confront the limits of intuition, the difference between description and understanding, and the possibility that the simplest questions, what is reality? Where does information reside? How does computation take place? May not have answers in the way we are familiar with. And that does not make science weaker, but makes it stronger, because it keeps us honest about what we really know and what we do not yet know. Perhaps in the future we will find a deeper theory, a new understanding that connects all these pieces together clearly. Perhaps we will understand the mechanism of collapse, or find an interpretation that does not require controversial assumptions. But it is also possible that the answer will never be as simple as we desire, and we will have to accept that part of reality always lies beyond human intuitive capability. What is important is not to stop at the search for answers, but to continue asking questions in a better, deeper, and more honest way. And that is where this story ends, or more precisely, where it opens up. The quantum computer not only raises questions about how we compute, but raises questions about the very foundation of reality. What we have seen is not a solution, but a series of suggestions, signs that the world may be far more complex than we once imagined. The real question is not whether we can build more powerful machines, but whether we can understand what those machines are revealing. And when you think about that, another question begins to appear. A question that is not easy to answer, but very hard to ignore. If reality is truly a computational process, then where are we in that process? And what is our role? If you want to explore more ideas that can completely change the way you look at reality, please hit subscribe to the channel so you don't miss the next videos. See you in the next journey, where we will continue to ask the questions that perhaps no one dares to ask.